Welcome to my poster. In the next minutes, I'm going to explain to you how chemical concepts and automated reaction exploration algorithms can profit from each other. If we want to develop a hypothesis for a reaction mechanism, we often fall back to the application of chemical concepts. For example, if we have a look at these reactants here, we might identify a nucleophilic site at the sulfur atom, while this carbon is electrophilic. Consequently, we suggest this nucleophilic substitution as a plausible reaction, which indeed is confirmed by the literature. Still, large-scale investigations in this manner are tedious. And that is one reason why we in the Raya group developed the software Chematon that allows us to explore reactions automatically. However, if there is no longer a human involved suggesting reaction coordinates to probe, where else shall we get these from? Brute force enumerations of reaction coordinates clearly result into a combinatory explosion, and even worse, many of the suggested coordinates won't even lead to feasible reactions. One answer to tackle this issue is to come back to the approach that we successfully used before. That means chemical concepts. It might be possible to identify promising reaction coordinates based on first principles heuristics, exploiting concepts evaluated for the reactants. However, due to the necessity to evaluate concepts only locally for the reactants, we must expect uncertainties in our reactivity predictions. To quantify these, large-scale statistical analyses are needed. Obviously, for such analysis, we need test sets, linking reaction coordinates with the resulting reactivity. However, with chemical concepts being such an integral part of chemist education, putting together such sets manually carries a high risk of bias. And this is where the circle closes. It is not only that chemical concepts might be useful to generate first principles heuristics to render automated exploration more feasible. Automated exploration algorithms applied in a brute force manner may also help us to put together less biased test sets for evaluating the predictive power of chemical concepts. They can propose reaction coordinates, and hence possibly reactions, that we might not directly think of ourselves. For example, for the reactants we mentioned in the very beginning, Chematon can easily find more than 20 different reactions. Further, as mentioned before, the brute force algorithm also probes unreactive reaction coordinates. While this is clearly undesirable in many applications, it is extremely valuable information to be included in our test set. Thank you for listening to my presentation, and make sure to also step by the posters of Jan Unsleber and Miguel Steiner if you want to learn more about Chematon.